started. We've got a number of practice problems coming up. Let me remove a couple. You'll see them back in a minute as we get to them. I'll leave this one on the side. That's the next one coming. Okay? But we're going to do the type one first. This should have been on Smart Site. You see the word bomb calorimeter, so it's that type of problem. It's a little bit difficult, more difficult than the one I showed you before because it has two steps in this one. Let me show you what I mean. The first sentence, which is the first 3 lines, is really the first set of calculations. We have a bomb calorimeter, and the equation for the bomb calorimeter is this. We're given Q 1.78 kilojoules, and we're given delta T 3.65. So the first sentence is actually having us calculate C, the heat capacity, so we can do the next calculation. Okay? So the only purpose for the first part is to find C, which is just Q over delta T, which is 1.78 kilojoules for 3.65 degrees C. It's going to be about 0.488, but we can just leave it as a fraction for now. We're going to need this in a future calculation. Okay? So now that we know C, we can start with the second sentence. And it's not a combustion per se, but it'll work because it's going to give off a little exothermic reaction. Let me write down the reaction first. The reaction is NaOH plus HCl goes to NaCl plus H2O. Does anybody remember from 2A the name of this reaction category? You can call this either a double replacement or a neutralization reaction. Okay? All right, we know that there's 50 mils of each, and we know it's 0.20 molar. Okay. Now, same calorimeter. Notice now we have a new delta T because it's a different reaction now. Okay, totally different reaction. Because the C is constant because it's the same calorimeter, but delta T changes because it's a new reaction, so there's going to be a new Q. So it's going to be the same sort of calculation. Let's just set up our math though more specifically. Okay, just like before, the sum of the Q's equals 0, and remember there's Q reaction for the calorimeter, and then Q reaction. This reaction, and then Q for the calorimeter. So there's two things going on. A reaction that's inside a calorimeter that changes temperature. So Q reaction will equal negative Q cal, which is negative C times delta T. Again, the C is going to be the same. Let me remove some of this other stuff here. The C is going to be the same. So Q reaction is going to be negative. C is up here at the top of the screen right now. 1.78 kilojoules per 3.65 C. And delta T now is 1.26 degrees C. So we're going to be left with kilojoules. I got negative 0.614 kilojoules. We're not quite at the answer yet, we're almost there. Okay, so here's the cube reaction. The negative means what? Blank thermic. Exothermic. Keeps going out of the system, being released. Okay, so we got that, but if you re-look at the question just one more time, it says what is the heat of reaction or internal energy per mole? And really you can say per mole of water, since in the products, water, it's the solvent, it's the main product. It would be easiest to do it of that. It really doesn't matter too much though for this problem. So how do you do the last part? And this is typical of bomb calorimeter questions, where there's one last step after you find Q reaction where you divide by a number. In this case, they want it per mole, so we have to find moles because we were not given moles. Okay, so we're going to end up dividing this number by moles, but first let's find it. Let's pick either reactant, it doesn't matter which one, and say, well, there's 50 milliliters. And let's just change this to liters, 1 liter per 1,000 milliliters. And now notice I can multiply that by the molarity, moles per liter. And so now I'm left with moles. This is moles of NaOH. Because it's all balanced and there's a coefficient of 1 in front of everything, that means this is going to be mole of sodium hydroxide, HCl, or water, it doesn't matter, because they're all a coefficient of 1 in the reaction. So it's mole of really whatever, 0.010 moles. And then you're just going to take these two numbers and divide them. Again, this is a pretty normal last step of a bomb calorimeter problem where they actually want it, say, per mole or per gram or whatever. You just want to go to the units they ask for. So in this case, it's going to be negative 61.4 kilojoules per mole, say, of water. And that's your final answer. Any questions on this problem? If no, we will go on to our next problem. This one involves the first law. How do I know that? You see a delta U, you see heat, and you see work. So this would involve the first law here. So what will we do here? Well, we're going to say as well the first law is delta U equals Q plus W. They want to know delta U, which is the internal energy. Q is 15.6 kilojoules, positive or negative? It's going to be positive. How did you know that? It's endothermic. That means heat is going into the system. Okay? Endothermic was the key word to tell us this is a positive number. Then work, 1.4 kilojoules. Is that a positive or negative number? Is work being done on the system a positive or negative? Positive. It's done on the system just receiving it. Okay? The key word here is the preposition on. Okay? Or the on the system, that phrase, that's the key to tell you this is also positive. So the answer is 17. Done. That's it. Okay? You just needed, the key part was to tell what sign this goes with what. So 17 is your final answer there. You can toss up the next question. This is the next one we had up. By the way, I think I mentioned this last time, but there's a bunch of first law problems if you need them. First law, YouTube 1 through 6 apparently. So plenty of those if you need extra first law problems. There's a lot of different variations on how they could look. I would consider this a pretty typical multiple choice question. Alright, let's move this out of the way. For this one, this is going to kind of set us up for the next chapter actually, pretty nicely. And you'll see as we do it how this works. We just actually want a total amount of heat. Okay, now let me kind of draw out what's going on here. We have water, liquid, at 22.5 degrees C. How did I know it was a liquid? This number is between 0 and 100. That's how I knew that. It has to be liquid water between 0 and 100. Okay, this cools down first to 0, and I know it doesn't say 0, but it has to cool down to 0 because this is where water is between a liquid and a gas. Wait, we're going to solid, yeah. Liquid and solid. There we go. So this is the freezing point, or the opposite direction, the melting point. And then it cools down to minus 10 degrees C, and this is water solid. I know it has to be a solid because the temperature is below 0, and 0 is the freezing point of water. Alright, so I want to sum up how much heat is released. So is this going to be endo or exothermic, by the way? To cool something down, I'm removing heat, so it must be exothermic. Okay, so there's 3 steps to this. First is, there's a Q, which is Cp delta T, and I'll call this Q1, I guess. Step 1 is cooling it to 0. So that's mass, 15.5 grams. Cp, just for fun, I wanted to do a problem in calories instead of joules. It's not unusual to see calorie units, so I'm going to do this one in calorie units, not joule units, just for fun. 1 calorie per gram degree C. This is a given. Cp is a given. And then, what's the first number that goes here in delta T? It's something minus something. 0 minus 22.5. Okay? So it's a difference. Make sure you get the difference. Turns out to be negative 22.5, but T final, make sure you know what that is. Alright, this turns out to be negative 349 calories. Are we okay that this is negative? Yeah, better be, because it's exothermic. Okay. Now, step 2, and we're going to get into this more in the next chapter, but you need to remove heat while it's freezing. But while it's freezing, it's not changing temperature, it's staying at 0. So it's going to get, for a phase change, its own Q. And again, we're calling this Q2, step 2. This is, well, right now I'll just say, for now I'll say delta H. Leave a little space here. That's a delta H for freezing. And I looked this up. This is negative 80.0 calories per gram. And again, this is going to be a given. That number right there. Okay? Now, I have to do something to this. Well, how do I have to change this? Because I can't use this number as is. It does not match with the first Q. I will have to multiply by mass to get pure calorie units. This will always happen where, and I'll put a little m here, mass times delta H, or sometimes it's a, just write it that way, moles times delta H. It depends how the units of delta H, you need to convert the units of delta H to pure energy units. Right now it's calories per gram, so I'm going to multiply by a mass. And the mass is 15.5 grams of water. That's how much water I have that I'm freezing. This turns out to be negative 1240 calories. That's for step 2. That's how much energy I need to go through the freezing point. Now we're going to have step 3. Step 3 is going to go from 0 to minus 10. Again, this is a temperature change now. We're back to changing temperature. So mass is still the same, 15.5 grams. Cp, what do you think? Is it the same or a different number than this one? It's going to be different because it's a different phase. Even though it's the same molecule, it's a different phase. Ice has a different heat capacity than liquid water. This happens to be 0.5 calories gram degree C. Again, this is a given. Okay, that you have to be given in the problem, or you look it up in the textbook if you're doing homework, something like that. Okay, what is the first number in delta T? Should say -10. That's the final temperature minus the initial temperature of 0. This is going to equal -39 calories. Notice again, we get a negative number, that's good. Okay, now I'm going to take this number, and this number, Q1, Q2, and Q3, and I'll merely add them up, and that'll be the total heat that is being removed. Okay, let's do that. Q1 plus Q2 plus Q3 equals -349 minus 1240 minus 39, and that equals, I got -1631, and this is in units of calories. That's my final answer. So again, it was just the sum of the total energy removed to remove water from 22.5, I think it was, to -10. Any questions on this one? Okay. This? Alright. Now, you might have, if you were here just a little bit earlier, seen this question. We're not going to do it right now, but I wanted to put it up when we walked into class, just so you get a head start writing it down. We're going to do that one momentarily. First, let's look at the schedule. Da-da-da. Let's move this out of the way a little bit here. And we're finishing chapter 11, starting chapter 12 today. Okay? I also have office hours tomorrow. I think it's in the syllabus. You need to find it by the South Lab building, 2064, 9:50 to 11:30, I believe. I already have an announcement on Smart Site, so you can check that out. Okay. I want to call your attention to the reader here for a moment. This is also, as normal, posted online, this figure. But let's just see what we did. So in this chapter, we did terms, we did work, we did the first law, we did the sum of the Q's equals 0, which is really from the first law. I just kind of worked a little bit on phase changes. You see that, the delta H, but we haven't done much with it yet. We're going to do more with it the next chapter. But we did several calculations with MCP delta T. You saw delta H, heat at constant pressure is delta H, and we're going to see some more delta H today. There's two ways to calculate delta H, and we're going to see both of those. Hess Law kind of method, and then the delta H formation method. Okay, so this brings us to the textbook, page 474, or the reader, page 14. Okay, let me do a little bit on that, and we'll do this problem that I had up just a moment ago. All right. This is Hess Law. What is it? Hess's law is a way to find enthalpy, or delta H, which is heat. We like that because it's energy. So really an energy of a reaction. And it's a way to do it when you're given simultaneous or consecutive reactions. Anybody vaguely remember those terms from 2A? Slightly? It's back. This is why you learned it. Every problem that you did in 2A regarding simultaneous reactions would 100% apply here. You need to do that exact same thing, and that actually helps you find delta H. Okay? So a simultaneous reaction, if you don't remember, is a series of reactions that will sum up to an overall reaction. So you know it's a Hess Law question when there's a lot of reactions given. See a bunch of reactions? Probably a Hess Law problem. Okay, let me do some mechanics of Hess's law first. Let's say you have reactants go to products, okay? And this has some delta H associated with it, and let's say that delta H is a positive number just for fun. If you flip this reaction, which you've seen in consecutive reactions before, you're going to flip the sign of the delta H to be a negative. If you take the original reaction again, and let's say you multiply by a coefficient n, not moles, but there's some coefficient, whatever that coefficient is, then you're taking the original delta H and multiplying by that coefficient. Okay? That's the mechanics that we're going to attach to what you learned in 2A from before. Okay? So those are the math of what we're going to do. Let's do a little bit on solving before we see an actual problem. Solving. There's different ways to do it. I have a particular technique that I like that has 2 steps. Okay? Step 1. You're going to ID a compound in the overall reaction that appears only once, one for once, in the simultaneous, that for simultaneous reactions. So you're going to find a compound that is in the overall reaction that appears also in the simultaneous reactions only once. And then you make those match coefficients. So you match coefficients once you do that. Or 2, this is the second step of my simultaneous, ID an intermediate. And again, you'll see a live example of this in just a moment. But first, does an intermediate appear in the overall reaction? Yes or no? No. You will not see an intermediate in the overall reaction. Does an intermediate appear in the simultaneous reactions? Yes, definitely. So you're going to something that appears in the simultaneous but not in the overall. That's called an intermediate because it disappears before you get to your overall reaction. You want to ID the intermediate, and then you're going to manipulate until it cancels. So in the first case, you're going to ID something that's in the overall, match it to the simultaneous, and then make sure the coefficients will match up. In the second, you're going to ID an intermediate and make sure it cancels when you add up the simultaneous. Okay, that's my method of solving. I actually follow this order typically. It tends to be the easiest. And now, let me show you an example here that I had up a little earlier. This is a pretty typical example. In this example, we want to find delta H. There's 3 reactions up top. Those are called the simultaneous or consecutive reactions. Each of those have a delta H with them. We're just calling them here delta H 1, 2, and 3. At the bottom, you see the overall reaction. That's the reaction we want the delta H for. So we're typically given the delta H for the top reactions and asked it for the bottom, the overall. Notice, or what you'll see in a moment, the top reactions will add up to the bottom reaction. Okay? We have to make that happen, but that's going to happen. And then you'll also notice there's extra molecules in the top reactions that don't appear in the bottom. That's what we call intermediates. So let's play this out with this example here and see how it goes. Okay, let's see. First thing I'm going to do is I'm going to look at the overall. This is my first step of the solving technique. Is there anything here, one of these 3 that appears only once up top? If so, which one? NO, I heard. Let's see if that's true. It appears once here and once there. That's a great place to start. And if you have a bunch of colored pens, this is a great place to use it. I'll put a purple box around the NOs. Okay? Now, remember the bottom one, the overall is what I want. That is the correct answer. So I must manipulate the top reactions. And so I have 2 of these here. Let's match it with this one. So I need to multiply this by 2. to have two NOs in the products. Thus, what will I do with delta H2? Also multiply by 2. Okay? Now, once I have a multiplier, I will not change that reaction. So reaction 2 is not going to change unless I find out I made a mistake. But who makes mistakes? Okay, is there anything else down here that appears only once above? Okay, I'm hearing some N2s. It appears once here and once above in the simultaneous. So a black circle for the N2 there, black circle for the N2 here. And this says 1/2. The hole punch kind of destroyed the 2 in the denominator. 1/2 of 2. Okay, so for that reaction, what do I need to multiply this by? 2, because if I multiply 2 times 1/2, I'll get 1 N2 in the reactants, which is what I want. So that means I'm multiplying delta H1 by 2. Okay, now you probably already noticed that O2 appears down here, but it appears twice up top. You can work with that, but it's going to be too much math. It's easy to make a mistake. So I prefer not to mess with O2. And because I've exhausted every compound in my overall reaction, I'm going to go to step 2 of my solving technique. That is, look for intermediates. So help me find an intermediate. That's something that appears not here, but only up here. What's an intermediate? Okay, I've got an H2 I heard, and that appears twice. Okay, what else is it? I'll list them down here. Intermediates. H2, what else? H2O, that's correct, it appears twice here. And NH3, I think I heard, it appears here and here. Now, even though NH3 is an intermediate, it appears in the two reactions I have locked down already. I prefer an intermediate in the third, so I prefer H2 or H2O. What's your favorite molecule? H2O is your favorite? Okay, good. So we'll choose that one. It really doesn't matter which one you chose. Let's do a brown underlined squiggly for H2O. All right. Now, H2O is different than the other ones. This one must cancel to have 0 in the overall. So right now I have, in the second reaction, 3 H2Os. So I have to multiply the third reaction by a -3 to cause the H2Os to drop out. A 3 in the second and a -3 in the third will drop that one out, which is really flipping the reaction. So thus I multiply delta H3 by -3. Thus, my final answer now, because everything has a multiplier, is delta H for the overall reaction is 2 times delta H1 plus 2 times delta H2 minus 3 times delta H3. And if we had numbers, we'd put those numbers in. Okay? So with those multipliers, now my simultaneous reactions will add up to the overall. Any question on this? So I've now completed what I wanted. I have the delta H for an overall reaction now, a new reaction that I didn't have before. Okay? I would consider this a medium to medium difficult question that could be a really normal question on an exam. Okay? So if you can do this, this is pretty good. This would be in the category of medium to medium difficult. I have a lot of examples online if you want to check those out. Hess's Law 1, 2, and 3, just for example. And then I have, just if you want to practice the multipliers outside of Hess's Law, I have simultaneous reactions, and then simultaneous reaction 2 and 3. So a lot of potential examples for you. Okay, let's move this out of the way. section 8, page 15 of the reader, page 476 of the textbook. This is delta H of formation. The little f means formation. The superscripted 0 that you see up there, or it looks like a 3 sign, you actually saw in the previous problem, that just means a standard state. So you're going to see that. That would be a standard pressure and 25 degrees C. It's just, it's a convenient state where people tabulate values in all these tables that you can look up. So you often see this, and that just means standard state. The little f means formation. Okay, what is this? This is the change in enthalpy to make 1 mole of a compound. So what is the enthalpy, needed constant pressure, to form a compound from its elemental form? So to form a compound from its elemental form. Let me show you an example. Just as an example here. Let's say I wanted to form a random molecule ammonium hydroxide. Okay? So if I want to form that, and liquid, whatever, doesn't matter the state, NH4OH. If I want to form that, that means it's a product, and I'm going to put a 1 here to be 1 mole. So 1 mole right there of that, I formed 1 mole of it. Now, what elements or elemental form compounds does it come from? Well, the nitrogen comes from N2 gas. That's the elemental form of nitrogen. The hydrogen will have to come from H2 gas. That's the elemental form of hydrogen. And then the oxygen elemental form is O2 gas. And I need to balance this again, keeping this key 1 right there in the products. So I need a 1/2 here. I need a 5/2 here. And then a 1/2 here. So we will see fractions in this kind of reaction because I need the 1 in the products. And the energy of this reaction would be the delta H of formation of ammonium hydroxide. Okay? So, knowing that you all are not always savvy on what's elemental form, in the reader, unfortunately the textbook, I didn't notice this having it. In the middle of page 15, I put this table. Here's the elemental forms. If you didn't know this, it was supposed to be in your brain already, but since it might not be, there it is. So, kind of get used to these as typical elemental forms. Okay, there's more, but these are the pretty common ones. Okay. So, I can use kind of this idea to find the delta H of a reaction, but I need to say one more thing. Delta H of formation of anything in elemental form equals 0. So if it's an elemental form, I don't need to form it, it already exists. So there's no energy to form it because it already exists naturally. So that means this one as elements by themselves, O2, H2, N2, would all have a delta H formation of 0. But anything not in elemental form, for example, this one, would not be 0. Okay? It would be some finite number. Okay, so I think, one more thing, and then we're ready to try an example of this one. So often we'll give you a reaction, and we'll ask you for delta H formation, or what delta H of that reaction. I already taught you the Hess Law way of doing it. In this kind of problem, you're only given 1 reaction. And that's how you know it's this kind of problem. There's only 1 reaction given. But what you're going to do with that reaction is something you might have done in high school if you've taken chemistry before. You're going to take the I'm going to use this term for sum. Oh, I guess you've already seen it before. The sum of the delta H of formation of the products and minus the sum of the delta H of formation of the reactants. Okay? So products minus reactants. I will have to multiply by the number of moles given by the coefficients in the reaction as well. And you'll see how we do that right now. Let me give you a reaction here. We'll try this as an example together. This would be a pretty typical problem. Here's a reaction, and let's say I give you a table right under it that has delta H of formation, and let's say this is in units of kilojoules per mole. Okay. Let me write these numbers down for you. Okay. This is also, these numbers, if you're doing a homework problem, are on table, I believe, D2 of your textbook, or on Google, Wikipedia, whatever. You look these up if you need them for a homework problem. On an exam, we have to give it to you in order to do this. I know that I'm not going to do a Hess Law solving method for two reasons. One, I only have one reaction, just the overall. Reason two, I'm given formation values. Well, there's a little subscript F somewhere. So it has to be this method, and here's how we're going to do it. Oh, by the way, why is no term given here? Yeah, it's 0. So we won't give you anything that's in elemental form. You should just know it's 0. A big hint would be if we don't give you the number. It's probably in elemental form. So what you're going to do to find the delta H of this reaction, you would go products minus reactants. What's something I would have to do first? Yeah, it would be nice to have this balanced. It'd be a 4, a 7, a 4, and a 6 will do it. So what I'm going to do is open big brackets here, and I'm going to say products first, 4 times 34, that's the moles of NO2, plus 6 times negative 286. And that's the sum of the delta H of formation of the products, including all 10 moles of the products. Now I'm going to subtract, open big brackets again, 4 times the delta H of formation of NH3 is negative 46, and then 7 times the delta H of formation of water, that's just 0, close brackets. A most common problem is people don't use these brackets and they don't distribute through the negative sign. That's a really common problem, just to mess up the math because they don't forget the negative sign on both of these. Okay, so this turns out to be negative 1396 kilojoules. That's the final answer. So it's a pretty quick calculation. Note one thing. The units changed. Where do you think the moles went? Remember, up above it's given in that table. The table is kilojoules per mole. Where did moles go? They went away. True. Because I multiply by the coefficients, which are units of moles. So the moles will always drop back. Okay. These tend to be much significantly easier problems for most students, but this would be a typical problem. Very normal, typical problem right there. So, in this chapter, I wanted to show you this. We're not going to cover section 9, which is the next book. You can read it for fun. But there are 3 ways to determine delta H that we've covered. Conversion, we did last time. We just did Hess's Law, and we just did delta H of formation. I believe I also have this in the reader too. It's just coming later. I believe it's like at the end of chapter 12 or something. I made a little table like this. Yeah, this is on page 31 of the reader. The reason I put this on page 31 is there's a bunch more ways to find delta H that we're going to learn in chapter 12. But just be able to tell the difference between these For example, the first one you may or may not have a reaction. The second one you're going to have a bunch of reactions. The third one you only have one reaction. So there's easy ways to be able to tell the difference, but these are all ways to find delta H.